Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 22nd, 2025. So, just under a week ago. This paper introduces a system that enables powerful 3D vision models to reconstruct kilometer-scale outdoor scenes, a task that would otherwise require over 1,000 gigabytes of memory. The paper is titled VGGT-Long, Chunk It, Loop It, Align It, Pushing VGGT's Limits on Kilometer-Scale Long RGB Sequences. And as we'll see, this simple approach allows it to outperform other modern methods without needing extra calibration data. And the community on X is really focusing on the core idea. They're highlighting how the simple chunking method solves the massive memory bottleneck, enabling efficient and scalable reconstruction at kilometer scale. Also, the authors shared their official implementation on GitHub. You'll find the complete source code, along with detailed setup instructions and scripts to download pre-trained weights. What's really nice is that it can run in a pure Python environment, making it super accessible for anyone to try out. And the results of this accessible approach are really impressive. The opening figure here tells the whole story. It compares VGGT-Long against 4 other recent methods on a kilometer-scale driving scene. You can see how methods like Fast3R and Cut3R suffer from severe drift. That's where small errors accumulate and warp the final map. Others, like the original VGGT, just fail to run the whole sequence due to memory. But VGGT-Long produces a clean, accurate reconstruction, and it does this across various datasets, even from an iPhone, without needing pre-calibrated camera details. So, how does it actually achieve this? This next figure visualizes the core chunk it and align it strategy. First, you can see the long video stream being broken down into smaller, individual chunks. Each one is processed into a local 3D map, which is the key to avoiding that massive memory overload. The bottom part shows how these pieces are then stitched together by finding consistent geometry in the overlapping frames between adjacent chunks. This alignment uses a robust process, focusing on high-confidence points like buildings, and relies on what's called a Sim3 transformation, a mathematical operation that precisely scales, rotates, and moves each chunk to fit into the larger global map. Building on that idea, this diagram shows the full system architecture. It has 2 parallel tracks. The top track feeds the video stream into the main VGGT model, which generates those local 3D chunks. The bottom track, meanwhile, uses a different model to perform place recognition. Basically, it's looking for moments when the car returns to a place it's seen before. This is crucial for what's called loop closure, correcting the small errors that build up over time. Finally, all the sequential chunks and the loop connections are fed into a final optimization step to create one globally accurate map. And this figure really drives home just how critical that final optimization step is. On the left, you see the map of before loop. This is what happens with just sequential alignment. The small errors add up, and the whole map becomes a tangled mess. The middle part shows the optimization in action. It's using what's called the Levenberg-Marquardt algorithm, a standard technique for finding the best fit to pull the distorted path back into a consistent shape based on those loop closures. The result, on the right, is a clean, globally accurate map. So we've seen the visual proof of that clean map, but let's look at the hard numbers. This table shows the camera tracking results on the KITTI dataset, using a key metric called absolute trajectory error, or ATE. This basically measures how much the model's estimated path deviates from the actual ground truth path. So, lower is better. What's striking is that other powerful models like Cut3R, and even the original VGGT, run out of memory on these long sequences. But VGGT-Long completes them all, achieving an impressive average absolute trajectory error of just 4.63 meters. To really understand what makes the system so effective, the authors performed this ablation study. Here, they take the system apart piece by piece to see how much each component contributes to that low error score. The columns show results when turning off loop closure, and a technique called iteratively reweighted least squares, which is a method for robustly aligning chunks by downweighting noisy data. Look at the first row. Without loop closure, the error on sequence 00 skyrockets to over 58 meters. Adding it back in drops the error dramatically, showing just how critical it is for fighting that accumulated drift. So those results really show how each part of the system is vital. In conclusion, VGGT-Long offers a clever way to scale up powerful 3D foundation models. By chunking video and using lightweight loop closure, it creates accurate kilometer-scale maps from just a single camera, a huge step forward for real-world robotics. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.